Meera Hahn and I will be presenting our paper, Where Are You? Localization from Embodied Dialog. Imagine trying to visit a friend who works in a museum for the first time and getting lost in the new building. Not sure where you are, you call your friend who knows the building quite well. You start describing your surroundings. I am standing on a red carpet, looking at a seating area. They may ask you to move or look around. Is there a round table in the middle of the room? So you start navigating in response to their questions and answer them. Yes, there's a wooden round table. After a few more rounds back and forth, your friend will hopefully know your location and come and get you. For future purposes, let us call the agent answering questions and navigating the observer, and the agent trying to locate the navigator, the locator. Success at this cooperative task requires active participation from both agents. Specifically, it requires goal-driven questioning from the locator, unambiguous answers from the observer that communicate observations. Oftentimes, it also requires the observer to navigate, both to investigate the environment and to seek out discriminative observations. In this work, we present Where Are You? Way, a new dataset based on this localization scenario. During data collection, we paired two annotators, one who acts as the observer who is spawned at a random location in a novel environment, and one who acts as the locator who is provided a top-down map. The map can be seen as a proxy for familiarity with the environment. It is detailed, often including multiple floors, but does not show the observer's current or initial location. The observer can navigate within their environment, but has no access to a map. For the environments, we use Matterport 3D dataset of 90 reconstructed indoor environments. In total, we collect 6,000 English dialogues of humans completing this task from over 2,000 unique starting locations. On the right is the histogram of localization error of the human annotators, which on average is 4 meters. Way is the first dataset to focus on localization. There are multiple vision language-based navigation tasks and datasets, but they all assume the agent is already localized. For example, in VLN, the navigator's location is already known by the agent giving instructions prior to giving directions. VLN also does not use dialogue. In the CVDN task, there is a use of dialogue. However, the remote agent assumes knowledge of the navigator's location at each step in the dialogue. The Way dataset and the localization tasks we introduced on top of it fill this gap by introducing a dialogue-based means to localize the navigator, which we can see as a precursor to tasks such as VLN and CVDN. Additionally, aside from finding the lost friends within a building, we can see the localization paradigm as being applicable to search and rescue settings where localization models could have the potential to help emergency responders localize callers quicker by identifying locations in a building that match a caller's description. Having presented the Way dataset, I'll now talk about the tasks it supports. The combination of localization, navigation, and dialogue in Way provides for a variety of modeling possibilities. We have identified 3 compelling tasks which are fully supported by the dataset. The first is localization from embodied dialogue. The input for this task is a partial or complete dialogue between the locator and the observer and a map. This input is input to a localization model. The model solves the state estimation problem of localizing the observer. This task can be evaluated using localization error via Euclidean or geodesic distance. The second task we introduce is embodied visual dialogue, which models the observer agent. The input is a partial dialogue, which ends in an instruction or question from the locator and a first-person view of the environment. The output is a navigation action and a natural language message back to the locator. The final task we propose is cooperative localization, which involves modeling both agents, having them communicate in natural dialogue, and finally outputting a prediction of where the observer's location is. In this work, we focus on the LED task. We model the LED task as a language condition pixel-to-pixel prediction task using a LinearNet skip model. The input of this model is a dialogue and a top-down view of the environment. The output of the model is a probability distribution over the possible positions from a top-down view of the environment. And we evaluate the task through localization error. We adapt the LinearNet architecture to fuse the dialogue and environment representations, Additionally, we introduced a language-modulated skip connection between the corresponding convolutional and deconvolutional layers. We train the model to minimize the KL divergence between the predicted location distribution and the ground truth location. Here we show the percent of successful localization in the environments unseen by the model during training. We define a success as a localization with under 3 meters of localization error. We use human performance as our upper bound. Then we show the LinguNet skip model's performance. We show that the LinguNet skip model outperforms ablations of itself, and we also show it outperforms simple non-learning based. In summary, we have introduced the WAY dataset with over 6,000 dialogues in 85 plus environments. We have introduced 3 new embodied localization tasks, and we have introduced the LinguNet skip model on the LED task and show it outperforms simple baselines and model ablations. But we have not fully explored the potential of the LED task. For instance, we use a top-down map, but future work does not need to be restricted as choice and may leverage RGBD panoramas or 3D reconstruction that Matterport 3D provides. Thank you for listening to our talk. To learn more, please check out our code and project webpage.